You know, this is the ball, right? When it's smashed into there, so that's like a fist. Boom. It's like a ball, rock. And it came down, right, into this other water that's contained basically another, you know, it's not part of this water up here, even though there's a slit, you know what I mean? This is a different whatever. So when you dropped into there, you made waves just like over here. I mean, put it this way. If I dropped this ball here, right, and there was a big rock shaped like this, right? Okay? So and this is all land here, okay? This is all land, all right? Now, if I drop the ball here, would anyone be like, how did it go around? How did it go around the sides? I don't understand. It's like it didn't, you know, would anyone say that? Would anyone really say that? Hey, I don't understand. It's like, how does the wave go around? It's like it's game. Not, you know what it did. It does what a rock does when you throw a rock in the water. You know, what the heck? How did it go around? How did the wave go around? It didn't go around. It went straight up. You freaking. It started out being as big as you are, right? And then it expanded because you are right there. You're right in the slit. You were right in the slit. And what happens if you did that here? It would do the same thing. The wave starts out being as small as the rock, right? So you don't see it, and then it comes out, out, out. Same here. You're at the slit, coming out, out, out. Why is it so mysterious? Well, when you do it with a particle, right? It's a tiny particle. We're not talking about baseballs. We're talking about something that actually vibrates a lot relative to its size. Okay, because relative to its size, a baseball doesn't vibrate at all. Okay, relative to its size, you can just say it doesn't vibrate at that point. It's so small. But you know, when this is the slit. I only drew one side of the slit. Right? There's two slits here. You have a fixed, you know, laser pointer or whatever you got, right? Shining their photons or whatever. Now, if photons, right, were acted like balls and they just went in a straight path, right? Then you would just have this type of interference pattern. There wouldn't be any lines in between because the ball could hit every place on this slit and every place on the wall. There would be no gaps, right? Because it's going in a straight line, right? Okay? Now what about over here? You got a fixed distance. You know, this laser doesn't move around. It's just stuck there. Now you've got stuff coming off. It's not coming off in a straight line. I mean, it is, but it's vibrating as it moves. So that the path isn't actually a straight path, is it? Right? So you have math telling you you're going to end up like this, right? Because there's some places you can't hit and you can't bounce off of because you have to hit these places at exactly, you know, the right point, you know what I mean? Because this one might hit it like that, but look up here. Sometimes they're hitting it in half waves. Let's say you go a half a wave up now. How can this photon, hit that half a wave up above this wave that hit the wall? You won't be at the end of the wave. If you ain't at the end of the wave, you know what I'm saying? That's why you have, you know, some spots where it hits and some spots where it doesn't. Okay? Because some spots he can't hit and bounce off and go to that area, you know, that on the wall, right? Not because it's a. See, the thing is, a wave and a particle that jangles and vibrates like a wave and makes a wave path, right? They get the same mass. They get the same probabilities. Don't you get it? Even though they're not really interfering in this fashion with a crest line up to the... Because if you do it with an electron, there's no crest in the troughs, okay? Well, I mean, there is in the path, but in the actual electron, it don't have troughs and crest or whatever. But all it is you're obeying the math wave function because your thing is acting like a wave by vibrating. You might look at this, right, and say, well, I don't think that wave equation is going to work for you because you're a particle and it's all about the path, first of all. It's not about being a particle or being a wave. It's about the path being a wave, okay? First of all. Secondly, we'll look it up. The wave equation says that it's good for any kind of, this kind of wave where you're, or this kind of wave, or if you're a vibrating solid, okay? If you are solid like a particle, right, like an electron, and you are vibrating, right? It says right in here, we're going to look at it right now, okay, that equation, that wave equation, is good for a particle, a solid that vibrates. You get the same response. If you have a particle, a solid that vibrates, right, and you throw it at something, it gives you the same exact probabilities, the same exact ones as if it was a wave, okay? And so that's why you can use the wave equation for it, okay? It's not because it's a wave, it's because it creates a path that looks like a wave. Well, it is a wave, its path is a wave. As you can see, it says the wave equation, right? Let's see what it says. They're talking about scalar wave equations, right? Solutions are for physical quantities in scalar, such as pressure in a liquid or gas, or the displacement along some specific direction, right, of a particle of a vibrating solid, okay, away from their rest positions, right? A vibrating solid. See, this is scattering, right? It's a scale. They're saying it could be a scalar wave equation. There's other equations they're going to talk about, right? And it's about displacing a particle that is vibrating, okay? And look at this. This is talking about a wave equation. They're talking about Hooke's law, right? That's a spring, all these things that they're direct equation and all that. Every one of them, if you look at their equations, I just started taking calculus, so I can't really explain everything, you know what I mean, when it comes to this. But I can tell you that I see oscillation in all their equations for this, you know what I mean? Because it's all about oscillations. It's all about going back and forth, you know what I mean? Just like a spring, right? Look at this. Spherical harmonics. It's an oscillation. They're talking about oscillation, where it goes out of the sphere. Again, in this one equation, spherical harmonics. Look, this one says the wave function, right? Again, harmonic oscillators. Quantum harmonic oscillators. I keep saying it, they keep saying about it, spherical harmonics. This is the wave function page on Wikipedia. They won't shut up about spherical harmonics. But it's not that they know it vibrates, but they just, instead of just saying that, they have to do all this crap where they're like making up all this magic. They both go through the same slit and they interfere with each other. They go both slits. They're all over the place. This is what I'm talking about. This is insane. The path integral formulation, right, for the double slit experiment can illustrate the path integral formulation of quantum mechanics. Now, how many times during this video series have I said the wave function does not represent the electron? It represents the path. And what's funny, it represents the path and the probabilities of the path that the thing takes, the electron. And here it is. And they're actually calling the integral a path integral. Are you kidding me? And then they say, no, it's not about the path though. No. It's about the light. It's about the electron. It's not about the path. Oh no. Then why'd you call it a path integral? But you notice what it's saying. Okay, let's shorten this sentence down because there's a lot of useless words in there. All right, this scalar wave equation. Okay, it's the solutions, right, are for things that are, displacement along some specific direction of particles of a vibrating solid. A vibrating solid. Okay, from their rest position. Okay, so they're saying this wave equation is perfect to describe a particle that is oscillating or vibrating, a solid that is vibrating. That's an electron. Okay, so why do I say that this, this right here it's a particle? And because it makes this path, it vibrates and makes this path, right? He will get the same probabilistic outcome. You can't use a linear equation because the electron isn't moving linear. I mean, it is in a way, but it's vibrating as it moves, straight. So that's why you can use this equation. That's why you get the same results down on the wall. And I want you to look at this sine wave, right? Okay. When it's going up, right? When something oscillates, right? When it's going, this is the rest position, right? So that would be right where it's at right now, right? Now if I pull it down, so it came down to here, right? And I let go of it, it's going to bounce up, bounce down, bounce up, bounce down, right? It's going to make the sine wave, right? But I want you to think, when it's on this dotted line here, right? That's the fastest it is moving, right? Because if I pull this thing down, okay, it's going to start going faster and faster and faster. Now when it gets to this part right here, it's as fast as it can go. Because then when it starts going this way, it starts slowing down, right? And then it gets slower, 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 slower. And then it goes, goes the other way. It gets faster and faster and faster. And then when it's at the midpoint on this dotted line, that's the fastest it's going, right? And then it goes slower and slower and slower, and so on and so forth, right? My whole point is that's the whole point of why you have to use a wave equation, right? Because here, every time you hit the wall, you're going the same speed. You're going the same direction, the same momentum, the same everything. But over here, even though you're a particle, you vibrate. And when you vibrate, you have a different, your velocity going this way is going to be constant, right? It's going to be the same, right? But going up and down, you're going up and down. Now that is a different story. Okay, because sometimes you're going fast, sometimes you're going slow, right? That's why you can't you can never use this kind of linear equation or whatever you call it when there's no vibration. Okay, put it this way: if I'm right, if I could take this photon, right? Let's say it's a photon instead of an electron, right? Unless I'm doing this experiment, right? If I could vibrate this slit, the black part, right? I didn't draw the whole slit. But if I could vibrate the slit, right, everything in the same way as him, right, so that, relative to each other, you're not vibrating at all, you know what I mean? If he's vibrating the same exact way he is, right, then they're vibrating the same exact way, you know what I mean? And it would just be a straight line going up here, and you would lose your diffraction focus, you'd end up with something like that. So let's do that experiment and see. Now you see up there how he has the fringes, right? Now if it's all about just being a wave, right? I say that it has to do with the vibration. Now that's light. So even if he hits one of these things that the light's going through, right? Taps it, vibrates it, right? Nothing should change. I mean, it might change, yeah, but as it goes, look at that. He taps it and it goes back. He vibrates it and it goes away. Okay, you vibrated it. See, look at that. He taps it, and it goes away. If he vibrates it, the pattern goes away. If he stops, look, he stopped, comes back. Now he taps the other one that light's going through, and look, went away. Interference went. Now he stops, and see. So is it tied to being a wave, or is it tied to vibration? Just like this clock. How is it acting like a wave? Oh, it's vibrating back and forth. How's this spring acting like a wave?